two means. Comparing two means isn't very different from comparing two proportions. You'll recall that at the end of Unit 6, we spent a decent amount of time comparing two different proportions. Usually this is done through subtraction. Means are the same way. The only difference this time is in the parameter that we're looking for. Before it was, P1 minus P2. Now, in this case, it's going to be mu1 minus mu2, or the two different population means. Now, since we still don't know the standard deviations of the two groups, generally speaking, we're going to estimate using the standard error using this formula. Now, you'll be using the calculator most of the time, and this will essentially be done for you, but you'll see it's very similar to the formula for standard error of two proportions. Essentially, it's the sample standard deviation for the first one squared over the first sample size, and then for the second mean, you take that sample standard deviation squared and divide it by the sample size, and then you take the square root of the entire quantity after you add it together, and that would be your standard error, which you would use in place of your population standard deviation. Now, since we're using two means, or we're testing two means rather, the confidence interval that we're going to build is going to be called a two-sample t-interval for the difference in means. And the corresponding hypothesis test is going to be a two-sample hypothesis test for difference in means. The assumptions and the conditions are all going to be the same as they were in both the last two sections, so we don't need to go back over them. If you do want to go back over them, please, if you're watching this, go back to one of the other videos. We review them in plenty of detail. Now, we need that standard error when we make a confidence interval because the way we make the confidence interval is going to be the same as it has been the entire time. We're going to start with a point estimate, that point estimate in this case being the difference in your two sample means. So whatever the mean from the first sample minus the mean from the second sample, that is what you start with. And then you're going to have plus or minus some critical t that you get from the table times the standard error that we just went over how to calculate. So the formula essentially would just look like this. Sample mean 1 minus sample mean 2 plus or minus critical t times the square root of sample standard deviation 1 over n1 plus, squared over n1 plus s2 squared over n2, all underneath the square root. Now, the critical t is going to depend on the confidence level and the degrees of freedom, just like it has before. We use a very special formula for that, which, as you can see, doesn't look like very much fun. So I'm never going to do this by hand, and you will never be expected to do it by hand. But if you want to calculate the degrees of freedom, basically it's this formula. I'll pause for a moment for any of you that really want to write it down for some reason. In this video, I'm not going to go over the actual calculations for a two-sample t-interval. I will post a link to that, or rather, I'll post that video next in the playlist, so you can watch that when you get a chance to. Now, testing the difference between the two means. So the hypothesis test we use, like we said, is going to be referred to as the two-sample t-test. Again, the conditions are the same, and when those conditions are met, this time the t-value can be found using this formula instead. So you find that critical t, or not that critical t, the actual t-value for your sample in this method. You see it's just the same t-score formula as it was before. The two difference in your sample means, the difference in your sample means minus the difference in your population means over your standard error for the difference in your sample means. Basically, estimate minus parameter over standard error. Same formula. And again, the formula for that standard error is there. And just like before, once we know that critical t, all we have to do is find it on the table, find the associated p-value with it, which tells us the probability of getting that test, and we just decide whether or not we're going to reject the null hypothesis or fail to reject the null hypothesis. And just like with proportions, the null hypothesis is almost always going to be that the difference between the two means is 0. And again, for this video, I'm not going to go through and post, or I'm not going to go and perform an example. That will be posted a little bit later, so this video doesn't run too long. But you'll see the actual mechanics of performing the test are largely the same as performing a regular old t-test, which again is pretty similar to performing a regular old z-test. Now we get to paired data. Paired data sounds like something that would be difficult, but in reality, it's not actually that bad. As a matter of fact, it's probably easier than two different means. So, as we learned back in our experimental design unit, data can be paired when observations are collected in pairs, right? You can set up an experiment where I think one of the questions we did on one of our tests was testing boot leather. You can have one foot have a certain type of leather on the boot and the other foot have a different type, so those two boots are paired the whole way, and you can find the difference perhaps in how the average length of how long the leather lasted before it needed repairs or something like that, right? Basically, you can have data that goes through an experiment paired so that you keep that data together. Paired data usually is going to arise when you have experiments that use a specific type of blocking, or you have matched pair units in the observational studies, like I mentioned before. Once we know that the data are paired, you can examine the pairwise differences, which is instead of the difference in the sample means, you can take each individual difference and find that average, and that could serve as your sample mean. So the difference that you're interested in isn't in the difference between one mean versus the other. It's actually the mean of the two differences between all of the data. And that sounds like it would be essentially the same thing, but the reality is that if you are able to do this, it actually makes your life a lot easier. The reason for that is because if you're only interested in the average of the difference, and you have all of those differences, then essentially each of those differences serves as its own data point, and you can run a one sample t-test rather than a two sample, and you're just doing it on the difference between the two data. So mechanically, a paired t-test is just a one sample t-test for the mean of the differences, where the sample size is just the number of pairs in the data set rather than the number of actual data points. So the assumptions for this are a little bit more complicated, but not really, right? They're mostly the same. You have to make sure your data comes from a normal population, just like before, or that it's nearly normal. But that has to apply to the differences rather than the data itself. So if you're checking to see if the normal condition is met, rather than checking the two different populations, you have to check to see if the difference is approximately normal, which if you have 30 or more differences, it's going to be anyway, or the differences must be shown to come from a normal distribution. Now, I have to double check. I'll follow up on this, but in Unit 5, we learned that if you have two different sampling distributions that are normal, and you subtract those two distributions, then the resulting distribution would also be approximately normal. So I'm not sure why that wouldn't apply here, but I'll go ahead and make sure. Perhaps it's a situation where they don't want, I'll figure it out. And the other caveat, if you will, for this type of data is that it's got to explicitly say that the data is paired, right? You can't assume that the data is paired together unless the problem tells you. And to be honest, I don't know why you would assume it would be paired together if the problem didn't tell you. You would be making up pairs as you go, and that doesn't seem like a good idea. We shouldn't make assumptions like that. That would be bad. When those conditions are met, we can go ahead and test the hypothesis that the mean of the difference is equal to some difference. In this case, this is the Greek letter delta, which is a stand-in for differences. And when you're performing this test, just like before, the difference is almost always going to be assumed to be 0, so not much extra work is going to have to be done there. And we use the standard t-statistic. It's just instead of x bar or y bar, you have d bar, which serves as the sample difference in means, or the mean of the differences, rather. Then you have delta, which serves as the population parameter for the differences, which again will almost always be 0, and then the standard error for those differences, which is just the same as standard error from before, but you have your own sample standard deviation used for the differences. After that, you just treat the same t like you would any other t, and you obtain a p-value that will help determine whether or not to reject or fail to reject the null hypothesis. So nothing really different there. So again, for paired data, there is no real difference in the performance of the test. You just have to know that you're performing a t-test on the difference rather than the actual means themselves. You run it like it is a one-sample t-test. You just know that you're doing it on the differences. So that makes it pretty easy. And as you might assume, if you're going to perform a confidence interval or you're going to construct a confidence interval for matched pairs, the format of doing that would be the same as if you were doing a confidence interval for one sample mean. You can have your point estimate be the differences, and you can add or subtract a margin of error, which is constructed of a critical t times a standard error, and again, there is that standard error formula for you. And just like before, the critical t depends on the confidence level and the degrees of freedom, which is your sample size minus 1. And since this is paired data, your sample size for both sets of data will be the same, so your n should be the same number, right? It's the number of pairs, not the number of individuals. And again, later on the playlist, I'll go ahead and post examples of these so you can see them perform for you, but I imagine not too much detail will go in there. And yeah, that's pretty much everything there is to know about difference in two means, both for confidence intervals and testing, matched or otherwise. Hope this was helpful.